Ethan St. Joan is a computer science major, and his concentration is data science. Last semester, Ethan took a course called Predictive Analysis, and this presentation came out of that course.
Thank you. All right, so as Dr. Alam said, my name is Ethan St. John, and today I'm going to be talking to you about the diabetic health indicators from a CDC data set that we got from online from a reliable source. It was the California Institute of Urban. And from this, we were able to use a logistic regression and other algorithms to kind of determine whether somebody is diabetic or not. So kind of the overview of the data set, there are a lot of feature variables that exist within the data set, but some of the main ones are high blood pressure, the BMI index of somebody, their age, their general health, as well as whether or not they've had a heart disease or attack in their past medical records. And then our target variable is going to be a binary feature variable called diabetes binary. And basically it's a 0 if you haven't had diabetes or if you've not been diagnosed, and then a 1 if you have been diagnosed. All right, so some of the preparation processes come out of data science, and one of the main things is cleaning your data and making sure that it's pre-processed for you to work on. And we didn't have to do any of this because the data set was from a reliable source, so they had already done all that for us, but this is the first step to take in any data science project, so I wanted to mention that there. All right, and then we can do some exploratory data analysis. So first we started out with just putting everything into R, the programming language, and from there we can make histograms, get summary statistics, and much more, which we'll see in the few slides. But to outline some of this information, R just lets us see all of our data at a glance. It's not anything that's super specific, but it helps us out. One thing I do want to notice is all of these statistics, they look like a lot of numbers, but they're very easy to understand. One thing about the diabetes binary data set, we see that it has upper quartiles, lower quartiles, and it also has a mean value. That mean value for a 0 or a 1 feature variable, that's not going to mean much unless you can understand that, well, if it's lower than half, that means most likely we have too many people that haven't been diagnosed with diabetes in the data set, and we're going to run into a problem later on with oversampling and undersampling. So we'll discuss that issue in a bit, but feature variable or feature statistics in R let you kind of see what you want to do with it initially. One initial impression that I got was the connection between age and high blood pressure. So using Tableau, I was able to throw the data in there, and from there make a box whisker plot. And we can see that the higher age ranges definitely have a higher blood pressure rating than some of the younger age ranges. And this age range 1 is from 0 to 24, 13 is going to be 80 years and older, and then it kind of just ranges in there between 4 to 6 years. This just goes to show that our information within the data set is accurate. It proves information that we already have as domain knowledge. And this is a heat map analysis, another type of analysis you can do. Basically, the darker the square, the more correlation two variables are going to have with each other. And then you can do chi-square tests to kind of prove that those do have a correlation. So we can see BMI and general health have a very high correlation, and they are statistically significant, as well as BMI and mental health. So I chose to do logistic regression for this assignment initially to start out. And through this, we were able to kind of get some base information about the data set itself and then create our model. So inside of logistic regression, usually you're going to have model coefficients, which predict likelihood, not probability, but likelihood in developing or being diagnosed with diabetes. And then you have significance tests, which are our p-value tests. They're going to tell us whether or not a variable needs to be included within the model itself. All right, so this is our logistic regression outcome model. We get some initial information about this. So the really long numbers on the end, the p-values that have 0.000, those are going to be statistically significant. So we'll want to include those within our model because they matter when it comes to diagnosing somebody as either a 0 or a 1. Some of the other ones that don't have stars by them, you'll see they're not very statistically significant, and so we'll take those out of our model to both save the time that it takes to run it, as well as just reducing the amount of information we might see off a summary like this. So something like high blood pressure, it's the first one under intercept over there. So based on the information we have, we know it's statistically significant, so we know that within 1 unit increase of high blood pressure, you'll result in a 0.79 increase in the likelihood or the log odds of being diagnosed with diabetes. And then we have something called the -2 log odds test. This is going to be to kind of confirm the ones we take out and see if they're meant to be taken out. So we can run a final model with all the ones we didn't need from initially, with all the unstatistically significant ones taken out. And then we test that against a null model and see how much the log odds decreases. And if it decreases by a significant amount, we know we did right because we took out all the ones that we didn't need. And we can kind of see there the residual deviance. Model 2, that's going to be the ones with all the ones I took out, and then the model 1 and then model 2 is the null data, or the null model. And we can see a residual difference between those of 1,400 to 1,100 or 1,000. Some of the key findings we had within this were high blood pressure, BMI, and the general health feature. Those are going to be reinforcing the medical knowledge we already understand as students. So basically monitoring and managing our health with these features are going to tell us what we already know. And then we had some surprising finds like mental health. Mental health going down actually increases your likelihood of being diagnosed with diabetes, and as well as higher income results in lower likelihood. So we can definitely discuss some of the socioeconomic factors that come into that later on, because the higher your income, probably the more access you have to better mental health professionals, as well as other less problems you'll have in the future. So we do an evaluation of our model. We can see the accuracy is really at 86%. We have a 97% accuracy in detecting negative results. So true negatives, that's going to be called as the specificity. True negatives are just you accurately didn't predict somebody, or you accurately predicted somebody did not have diabetes. But if we look at specificity, specificity is kind of it's low. So that's because we have a lot of non-diabetic people in our data set. This is going to cause us to have very low true positive ratings. And there are a couple things we can do to fix this. So reevaluating is the next step we'll take, and model based on I'll get to that, sorry. The potential strategies we can use are to overfit or underfit the sample, which is what I chose to do. There are also other algorithms, such as SVMs and random forest sampling algorithms, that allow you to work with the imbalance or the unstructuredness of the data set there. And then you can also, okay, no, I discussed those, sorry. And then comparison of the results, we see that the accuracy decreased a little bit. It went from 86 to 78, but our sensitivity went up by a great amount. And basically the question then comes, was it worth reducing our accuracy and a bit of the specificity to increase our sensitivity or our true positive, our accurate telling somebody they have diabetes? Is that worth it? And in my case, I found that it was, because early detection is some of the best ways to prevent diabetes or to get help the fastest, so that you don't end up without help later on in the future. Lifestyle changes can be made, medical interventions can be also taken under if you need those, but a low sensitivity increases the risk of the false negative that I was talking about, so we don't want those. In a world of diabetes, false negatives put somebody at risk and eventually could cause death. So some of the implications that we have are public health can kind of take this and make more awareness about it. A way to say it, you can create different campaigns or different ways of promoting healthier lifestyle and less riskier lifestyle choices that you can make based off what we've seen from how significant something is. There's also resource allocations, so if there's certain things that aren't being put into, like for example, smoking had a lot of, or didn't have a very significant value, but a lot of money is put into non-smoking ads. So maybe we focus more on, or shift allocations of resources to maybe BMI help for underage or underprivileged students. And then future research always comes into question at the end of our tasks, so we can definitely incorporate temporal factors. That's going to be us incorporating the ability to read data from not only what we have in the past, but data that we collect over time. And we can also integrate with clinical data, so working with other healthcare professionals, we can integrate their data and get more accurate results. This will also help with the overfitting and underfitting problem. So if we have more results that are recorded as diabetic, that would help us fit more into our model and fit better with a true positive rating. And then there's my works cited. Were there any questions?
I think we can have like 2 questions.
What's the biggest surprise to you in your findings?
The biggest surprise was probably the income, though I could expect it based on where we live and the political factors that affect us now as students and also as adults. But I didn't think the income would be as important as it was to our model. So I guess the sensitivity of income.
Any more questions? No? If not, let's thank our speakers.